I am the lead developer on the DAHDI project. DAHDI is a set of open source Linux kernel drivers for various types of telephony hardware. It's basically what connects Asterisk to the physical world. Aha. Okay, so in my talk today, I'd like to talk about T1 and E1 technology, where it's been as a history, where it is today, and all of the bits and framing and coding and stuff that goes along with that. We'll talk about the history. We'll cover framing and coding. We'll talk about loops and how they're used. We'll talk about alarms, what they're used for, the two types of signalings. We'll talk about how timing is propagated in the whole system. And we'll walk through DAHDI and see how data gets from the line up through DAHDI and into Asterisk. OK, 1876, the very first Astricon. Check out these, like they all have handlebar mustaches that I wish we did too, to be honest. But seriously, this is Graham Bell. This was the very first phone call, and back then, phone calls were analog end-to-end. You had operators plugging people together with patch panels. 1985, the Unholy Alliance. AT&T with US government formed a government-controlled monopoly, allowing AT&T to control the long-distance network for the entire nation, monopolied, but the reason for this was so that end users wouldn't have to worry about compatibility with their phones. Can you imagine if a company had this today, complete monopoly over a technology that everybody uses? 1947, two guys watch as another guy pokes his eye out. This was actually Bell Labs begat from AT&T monopoly. This is where they invented the transistor. Transistor was actually a direct result of telephony research that they were doing. 1964, this was the first comma alio. Right, classes in the room. This was the #1 electronic signaling station. This was introduced at the 1962 World's Fair by AT&T. This was the first huge application of transistor technology. And this is the first automated call switching system, basically. So this system is what took the place of all the ladies with the patch panels, like connecting people together. And so I guess they lost their jobs.
And based on AT&T service, it's still in use today?
Yes, in fact, the predecessor of the 1ESS, the 5ESS, is still used today. And in fact, there are about 41 ESSs still in use, according to Wikipedia. And oddly enough, they mention it's mostly around Atlanta. So maybe we could find one if you guys care. I don't know that I even care that much. OK, 1960s, we invented TDM technology. AT&T moved its interior trunking from frequency division multiplex to TDM, and this allowed them to double their capacity like overnight. This was the very start of T1. 1984, the divestiture. This is when the government finally said, hey, AT&T, we've had enough. They broke them up, let AT&T have control of the long-distance network, and then broke up into little companies to do local service called Baby Bells or RBox. This was the first time that the public had access to a T1 line because AT&T had to make it available for other companies. In the 90s, we ended up kind of having like an information renaissance, right? We started getting all the interconnectivity, and by the late 90s, AT&T said that more of their network was being used by data than by voice. And this actually gave us some upgrades to the technology. I'll explain that a little bit later. Okay, so I'm an engineer. I'm not a market analyst. But I find myself having to justify this talk to a lot of people. So I wanted to talk just briefly about market penetration. Okay, so I did some research. This company, Infinetics, did a survey of 300 enterprise companies. 71% of them responded that they used T1 for their telephony trunking. 38% responded that they used SIP. So if you don't think that T1, E1 stuff is relevant today, well, it was a US research. But thanks. I'll get you back, Tori. OK, all right, so let's actually start talking about the technology. First thing we need to do is take an analog voice signal and turn it into a digital signal. Now, I imagine most people in this room know how to do this because it works with SIP the same way that it works with T1. But I'll just cover it really quick in case somebody doesn't. So what we need to do is, as the analog signal comes in, we will take amplitude measurements of the signal at periodic intervals. Okay. Let's say we've got some time t. We take a measurement of our signal. We'll map it to some 8-bit sine value, and that will be the amplitude of our signal at that time. If we get enough of these signals samples together, then we can accurately reproduce the signal at the other end of the digital line. Actually, there are two questions that you need to answer when you think about this. One is how often you want to sample the waveform. And that was answered a long time ago, back in 1924 by Nyquist, who was also with Bell Labs, called the Nyquist theorem. And for analog telephony, the rate that everybody uses, even today with SIP, is 8,000 hertz. The other question that you want to answer is how you map voltage to the 8-bit sine value. Now, you might think the easiest way to do this would be to just assign it evenly, okay? But it turns out that you can improve the dynamic range of your audio if you focus more on the zero crossing line than out here at the extremities of your amplitude. There's two algorithms that do this. It's called companding. And of course, if you're in SIP, you know what this is, G711. Obviously, T1 uses mu law companding. E1 uses A law companding. They're close but not compatible. Okay, so let's start putting data on the line itself. For small networks, it's sufficient to set a binary 0 as a 0 voltage on the line, set a binary 1 to some positive voltage on the line. In your smartphone, it's probably some 1 volt. In T1 and E1, it's actually about 3 volts. But you run into problems when you extend that network out because you can get electromagnetic interference. So you need some way to code your data such that you can kind of detect if there's problems on the line. And both T1 and E1 use the same type of coding, fundamentally. It's called alternate mark inversion. Okay, so in this example, a mark is a binary 1 on the line. Okay, so every binary 1 that precedes another binary 1 is reversed in polarity. Okay, so I've got a 1 bit here that's positive 3 volts. The next bit that comes in is going to be negative 3 volts. The next bit that comes in is going to be positive 3 volts. So if data goes missing, then the receive side knows it because, hey, I got 2 of the same polarity voltages. Something's wrong. I must be missing a bit. And this is referred to as a bipolar violation. Okay, so before this slide, T1 and E1 is synchronous technology. So two pieces of equipment that are talking to one another have to have the same clock rate. Okay, so if they don't, then one end is going to be sending data faster than the other end receives it. And this causes slips. This causes data loss, buffer over and underruns, and is generally not good. This is actually the biggest problem with T1 and E1 as far as solving it from an engineering perspective. Okay. So what happens is in a network, you'll have an upstream and a downstream, and the downstream is going to derive its timing from the upstream. Okay, and it does this by watching state transitions on the line, plugging those state transitions into something called a phase lock loop, and that phase lock loop times the local machine. Okay, and so that timing will stay in sync with the machine that's upstream as long as it has state changes. Okay. So there's a problem if for some reason the data is all zeros. We won't have enough state transitions to keep our local time in sync. Okay, so this gives us our ones density requirements for both T and E1. So to solve this without changing the data, we inject intentional bipolar violations into the line. This gives us state transitions without affecting the data, because when the receive side sees these two intentional bipolar violations, it's watching for them. It takes those out and replaces them with zeros. So for T1, we use BAZS, that's bipolar 8-0 substitution. And for E1, we use HDB3, something bit 3 code. Okay, anyway, for E1, instead of 8 bits replaced with a bipolar violation, it's just 4 bits with a bipolar violation at the end. Okay, so we've done coding. We've talked about 8 bits per sample. Now we need to organize our times.
So when you get a bipolar violation, you just get that bit and carry on, or?
Okay, so the bipolar violations are inserted intentionally. The receive side is watching for this specific code word. It always looks exactly like this, with 2 bipolar violations and 2 other bits set. The likelihood of this happening on error in your line is very low. It's very low compared to the bad things that would happen if you got all zeros and your timing goes out of sync and you start slipping a bunch. Okay, so now we're basically putting bits on the line one after another. We need some way to frame this data, to organize it such that the receive end knows which byte belongs to which time slot. Okay. So we do this in T1 by appending a frame bit to the start of our 24 audio samples. I say audio, it could be data, so whatever. But so in T1, we've got 24 audio samples. All of these samples are sampled at the same time, and then it repeats itself, and then that'll be the next sample for all your audio data. Does that make sense, everybody? Okay. So for T1, there's a frame bit in the beginning, and then this is referred to as a frame. Now in E1, actually E1 was pretty much a wholesale improvement over T1. By the time E1 was invented, there had been all the lessons learned with T1, and it's better in almost every way. So for E1, we've got a faster speed. That gives us more time slots to put data into. But also, unlike T1, we've dedicated an entire 8 bits, an entire time slot to channel management. Not channel management, line management, basically. Framing, coding, etc. Oh, let's see. Okay, so the original type of framing for T1, super frames. Okay, so we've got a bunch of frames on the channel. We use our frame bits to determine where we are as far as time slots are concerned, right? So a super frame is a collection of 12 of these frames. Now you can't just put a 1 in the frame bit and expect to use that because there could be a 1 anywhere on the line. So what we do is we encode this code word into the frame bits called a frame alignment signal. The receive end looks for this code word, and once it sees it a number of times, it can lock on to the super frame, and then from there it knows exactly where the channels are. Oh God. Okay, so extended super frame was an improvement on super frame format. Okay, so as the years go by, we realized that we didn't actually need 12 bits per 12 frames to synchronize our data. We actually only needed 6 bits per 24 frames. So super frame is a collection of 12 frames, 12 bits for framing. Extended super frame is the same thing, except it's a collection of 24 bits. Okay, so I've kind of organized this oddly, but upper left is bit 1, frame. And then lower right is bit 24 of the frame. Okay, so we can see that our frame alignment signal rides in every 4 frame bits. Okay, and there's a lot less of them than in super frame. So that gives us all these other frame bits to do fun stuff with. The first improvement was to add a CRC6 check. The way CRC6 check works is when you transmit an extended super frame, the CRC6 is calculated and then appended to the next super frame that goes out. So the receive equipment will need to buffer an entire extended super frame, read the next CRC6 bits out of the next extended super frame, and then determine whether or not that frame passes its CRC check or not. And now we've got 12 whole other bits to do fun stuff with. This is called the facilities data link, or just data link. In extended superframe, alarms, maintenance requests, performance counters, all kinds of fun stuff can be put in this data link. I think it's fun anyway. Okay, so E1 framing. Now, if you remember, E1 doesn't use frame bits. E1 has an entire channel, time slot 0, dedicated to its framing. Right? So in E1, the frame alignment signal repeats every other sample. And there's also some supervisory bits over here that kind of do the same thing. But E1 also has an optional CRC4 check. Those CRC4 bits are over here where it says C, if you can read it. And it's exactly like T1. The CRC4 checksum rides one. These are actually called multi-frames behind the one that it's actually checking. However, E1 actually adds a response mechanism called E-bits. So if I receive a broken CRC4 sub-multiframe, as indicated by using the CRC4 to check it, I will set one of the E-bits back upstream so that the upstream provider will know that something's going on with the transmit side. The remaining bits are called the non-frame alignment signal, and it's almost exactly the same in T1 as the data link or facilities data link. It carries maintenance requests, looping, alarm states, except for the E-bit, and performance measurement. Okay, so to me, the most confusing thing about this is the dumb names that they came up for alarms. All right, so we have two types of transmitted alarms, the remote alarm indication and the alarm indication signal. Okay, so the remote alarm indication, this is actually what we refer to as a yellow alarm. Actually, before I start here, a red alarm is not defined in the spec because a red alarm is a local state only. A red alarm is your device telling you, hey, I'm not receiving data for some reason. Okay, I'm not synchronizing on the line. Okay, so a yellow alarm is a transmitted alarm. If for some reason I stop receiving data, I go into red alarm, right? I don't know that my transmit is broken. It could just be the receive side that's broken, okay? So I'm going to send a yellow alarm to my upstream device and say, hey, I'm in yellow, your transmit appears to be broken. This way we can kind of maintain some path of communication without just tearing everything down. Okay, so blue alarm. Blue alarms are pretty rare, but I'll talk about it anyway just because it's part of the spec. So same scenario as before. I'm a device and my upstream trunk has stopped sending me data. For some reason, I'm not getting anything on the line. But in this case, I also have a downstream device that I'm talking to. I'm passing data back and forth. In this case, I can actually send a blue alarm, which is an alarm indication signal, downstream to my downstream device. That way, I kind of indicate to him as well that something's going on with the upstream link, but I don't know what's going on. Now, the reason we actually do this is because of the ones density requirement. Instead of taking down the entire link, I can send unframed ones, which is a blue alarm, and the device that's downstream of me can maintain its phase lock loop on that blue alarm code without going out of timing. Tori?
Would there be a higher level of Russ lessons apart from blue alarm? Just how do you know what's going to be the next hop?
A blue alarm is only one hop. It's going to be transmitted to whatever device is downstream of me, but he's not going to propagate the blue alarm. Well, he might, actually. Yeah, I guess he would have to. Klaus?
So which of these three devices is now in the state blue alarm? The middle or the right?
It really depends on what you consider in state, okay? So this guy is transmitting a blue alarm.
I mean, if I use the DAHDI tool, it tells me you have a blue alarm or a red alarm or a yellow alarm. I'm always confusing now, is this now a problem with my card or is it something I receive from the others?
It's upstream. Both of these alarms are received, are a received type of alarm. A red alarm is just a local state. Does that make sense? So in this case, when DAHDI says, hey, I'm in yellow alarm, You would be this guy because your transmit's broken. In the case that DAHDI says you've got a blue alarm, you would be this guy.
What if there's a third box connected? Will both boxes be getting a blue alarm if the third link is broken? Or?
Oh my God, Tori. Where would it be connected? Where would the third box be?
But you can have a box can have more than one E1, right? So this box, the middle box has two E1s connected to it. One.
Oh, no. I'm sorry. This is the same link. An E1 consists of two pairs, a transmit and a receive pair. They're fundamentally disconnected from one another. In fact, that's why these alarms exist, because one side of the pair could break, the other side could still be up.
The middle box is an E1 going to the first party and an E1 going to the second party, right?
Oh, right. It just depends on how your network topology is set up. Who you consider downstream, who you consider upstream. Likely not.
Maybe they're asking about, I have two different links.
Right.
And can one link need a transmit a blue signal to the other link? It's not this, right?
Right.
8 ports on my board
Right.
has individual alarms. Not bypassing alarms.
That's correct. And typically you won't see this because asterisk is usually an endpoint device. Right. Loopbacks. Loopbacks are my favorite. There's a utility in DAHDI tools called DAHDI main that can activate these loopbacks, by the way. So loopbacks are codes that you can send down the line that remote devices respond to help you test the network, basically. So a line loopback tells the remote end, hey, I want you to send all the data on my transmit line back to my receive line. That way, you can kind of test the physical line itself. A payload loopback tells the remote end to go ahead and process the data that I'm sending it, but put that data back in the time slots coming back towards me. All right. This is handy for testing if the remote end is configured correctly, because it has to process all that data. Whereas with a line loopback, it doesn't process any data. It just basically shorts the lines together, and it goes back to the upstream. And then a local loopback is not actually part of the spec, but it's the most handy thing ever. It's the most common loopback that I use when I'm doing DAHDI drivers, because you can put something in a local loopback, send pattern tests, and it immediately comes back to your receive side. This is roughly equivalent to plugging a loopback cable into your span. It has like awkward syntax that I always forget, even though I wrote it. Okay, so there's two types of signalings we need to talk about. And again, confusing nomenclature. We've got channel. When am I supposed to end? Does anybody know? Sorry? I was 40 to 12:15. Oh, sweet. I can bore you guys for like 10 more minutes. Two types of signaling. Channel-associated signaling, CAS, and common channel signaling, CCS. Okay. Let me start with common channel signaling, okay? Because that's the most modern signaling. That's likely what you're going to use. Common channel signaling is PRI, essentially. What common channel signaling does is it takes a time slot, it assigns that time slot to be a data channel that some upper level library can then handle signaling for you. That's what libPRI would be doing. It uses a single time slot as just a data pipe, and it talks to some PRI thing on both sides, and they handle channel signaling management. The old style is channel-associated signaling, or CAS. Okay? The reason this exists is because T1s and E1s want to pass analog signaling like handset, hook states, ringtones, and stuff like that through the digital network and onto some analog thing on the other end of the network. Okay? So let me go through the analog. This is referred to as analog signaling. Or at least that's what I call it. Okay, so it's actually different for E1 as it is for T1. Okay, so in T1, it's called robbed bit signaling. And the reason it's called robbed bit is because, okay, so these are the frames of an extended superframe. In the 6th, 12th, 18th, and 24th frame, we rob the least significant bit of every time slot. Okay? We use that bit to generate this ABCD message. And this ABCD is basically a state diagram of what the analog hook state is. Okay? So this is no good for data applications, obviously, because you can't just steal data from, I don't know, your 56K modem with V90. Now in E1, there's no such thing as raw bit signaling. Doesn't exist. Stop asking me. In E1, channel-associated signaling, time slot 16 is dedicated to transmitting the ABCD bits. Okay, so all of the channels are what we refer to as clear. They got their full 64 kilobit per second rate. You're not taking any bits from them. It's all in time slot 16. And it's actually specified to be time slot 16. So if you wanted this to be on something other than time slot 16, you're out of spec. And you're out of order. Okay, so timing. All right, so as I mentioned before, it's so important that your T1 or E1 device maintain timing with a public network. This is because they have to remain in lockstep. If your clock wanders at all, then one device is going to send more data than you can handle or less data than you can handle, in which case you have to inject fake data or just throw away data. Okay? So basically, a public network provider, such as AT&T, will have something called a primary reference source. This is like a super, mega, ultra accurate clock that it times all of its routers off of. So if you connect to AT&T, public network of some sort, you're going to want to recover timing from that because you'll be on one of these stratums. Okay, the stratum numbers are actually your degree of separation from the primary reference source, and it's defined in the specs how many slips are going to occur because you get less and less clock quality as you go down in degrees of separation. The only case in which you would not want to recover timing is if you have an isolated network. So say you've got a SIP trunk coming in, and then you've got like a T1 or E1 channel bank, and it's not connected to anything else with T1 or E1, then you would want to provide timing in that case so your channel bank can synchronize properly. I guess there's other cases, but that's probably the most common case in which you would not want to recover timing. Okay, so here's DAHDI stack. So at the bottom, we've got our physical T1, E1 lines coming in. We've got some hardware here that does the fun telephony stuff. Okay, and then we've got DAHDI, and then we've got our user space stuff. Okay. So how the stat works? Some T1, E1 packets. Some audio comes in, a frame comes in to the framer. The framer is sort of like the industry, what we call the chip, fully integrated these days, that handles everything to do with the physical layer of T1 and E1. Okay? That framer is going to move the time slot data into a DMA engine, also on the card, typically in an FPGA, CPLD, something like that. And that DMA is going to move the time slot data into main memory automatically. The base driver controls everything that's specific to the hardware itself. Okay, it's going to set up the framer, it's going to set up the DMA engine, CPLD, whatever you've got on there. It's going to set all that stuff up, tear all that stuff down, and then call back into DAHDI-base.c for passing the data up the stack, the time slot data. DAHDI-base.c is common to all of our base drivers. And it wasn't until I created this that I realized that that's actually kind of confusing nomenclature. So DAHDI base handles all of the generic telephony stuff, and it also generates the user interface to user space. It lists a series of ioctals, which are system calls into the kernel. It generates files, it generates things that generate files, and it acts as the interface between the hardware and user space. Okay, so with the ioctal and files in place, you can now just generate a file descriptor for the channel that you're interested in, And then writing and reading from that channel is just writing and reading from a file itself. Okay. Whew. 3 minutes. Okay, so we talked about the history of all this junk, coding, framing, why you would want to use loops, how alarms work and how confusing they are, the two types of signaling, how timing works, and how the stack works in DAHDI. And we're done. Any questions? Excuse me while I take an extreme moment.
When you have multiple links, when you have like 24, 64 A1s, how do I synchronize different companies? Like I have telephone companies that one give me 8 spans, the other one give more 2, the other one give another one, and each one of these companies has different timing. How do I configure like the timing sequence and whatever?
Okay.
I had a very hard time synchronizing above the second one because the first one is locked. I don't have any time slips, but the second beyond, all of them are slipping.
Sure. How do you synchronize multiple timing sources? Actually, T1E1 technology is not synchronous. It's something called plesiosynchronous, which is like almost synchronous because it has facilities that deal with timing slips. Okay. Your problem is very specific and very hard one to solve for us. So I'll talk to you more about it afterwards. But just as a side note, your multiple different carriers should actually be in phase with one another. The reason you're having a problem is because they aren't. There are some tricky things you can do with timing cables that connect from card to card, but that's very esoteric and very not applicable to most folks.
Different things between companies.
Yeah.
It's a nightmare.
I know, it sounds like a nightmare. It really does. Any other questions? Everybody just hungry? No, not Tori. No. All right, Tori.
It's just a quick one. Could you repeat what the difference between the remote loopback and the payload loopback again?
Sure. A remote loopback asks the, well, I don't need the diagram. The remote loopback asks the other end to basically short transmit and receive before it does anything to the data. Okay. So whatever I send on transmit line, when I send a remote loopback, is going to come back on the receive line, but it's going to travel the entire distance to the other side. Okay? A payload loopback, the remote side is going to process that data through its stuff, through its framer, and it's going to put the data that's on the time slots back in its own time slots and send it back out. It is getting reframed. That's a great way of putting it. Klaus?
All the time slots or just the signaling time slot? Sorry, what is looped back exactly? Is it just signaling time slot or also the data time slots?
It is the data. Well, it's actually all of the data, all of the framing. There is a spec for E1 that allows single channel loopbacks. DAHDI maint doesn't currently support that. I've never had anybody actually want it, but we could do it if we wanted to. But it is the entire data payload.